Cycle time is a challenge that every molding company comes into contact with. We always want to make our cycle as productive and efficient as possible, but how does that impact the part quality? It's an important trade-off that we always have to consider. Our first case study from Yuki is on a sewage tank for a carpet cleaner. This is a relatively large part, and so the cooling time is very sensitive to the temperatures that we apply in the mold. In this case, a deviation of 30 degrees on the cavity could cause the cooling time to extend all the way out to 120 seconds. Because of the design of the cooling channel around the hot runner, we see that the heat is retained in the mold where there's not a cooling channel present. The solution is to improve the cooling channel circuit around the nozzle, and so there is no more of a substantial hot spot created in that area. In this case, because the part surface temperature is able to be more uniform, the cycle time is able to be reduced significantly. In this case, the cooling time was decreased by about 75% from 120 seconds down all the way to 30 seconds. Our second case study comes to us from Volstapine, who's studying the temperature distribution in a mold insert for the inner shell of a washing machine. And the challenge here is that we need an insert that has good wear resistance while also minimizing the cycle time. The cooling result from a beryllium copper insert shows that the temperature is able to be extracted because beryllium copper has such a high thermal conductivity. It was originally thought that just a simple cooling channel routing through this insert was enough to extract the heat. Although, if we look at the temperature distribution from the simulation, we can see that the heat is accumulated in certain areas of the insert, causing a temperature variation across the surface of the geometry. The solution is to make a much more complex conformal cooling system to remove that heat more uniformly. We can also then use a lower thermal conductivity material that has better wear resistance so that this mold is applicable for a longer amount of cycles. In this case, we were able to switch the material from a beryllium copper to a stainless steel using this conformal cooling design. And because of this more uniform temperature distribution, our cycle time was able to be reduced significantly. To verify this, 3 sensors were placed inside the metal insert to compare the simulation results with reality. And the graph on the right side shows a great thermal comparison between the simulation and the real molding process, indicating that the simulation results reflect what's happening in the real molded product. In this case, we're able to change from a beryllium copper insert to a stainless steel insert while making the temperature much more uniform. Generally speaking, moving from a beryllium copper insert to a stainless steel insert increases the cycle time significantly, but because of the conformal cooling layout, we're able to maintain the same cycle time and part quality while increasing the life of this insert.